So, welcome to the Computational Math Seminar today. So today we have Luke Owens visiting us. He got his PhD at South Carolina. He's at Texas A&M as a postdoc right now. And today we'll talk about an algorithm for surface encoding and reconstruction from 3D point cloud data.
All right. Thank you, Dr. Brenner. All right. So, as mentioned, I'm going to talk about an algorithm we came up with for surface encoding, and then we also reconstruct the surface. And our data is just 3D point cloud, just X, Y, Z, no normal information or anything like that. All right, so we'll start introduction, give you problem motivation. Why are we working on this to begin with? Some of the data sets that we work with, and I'll maybe point out some of the challenges with these data sets. Our algorithm outline. And then I'll go over our encoding algorithm, which is sort of where the bulk of our work has taken place, or we've worked on so far. We have an adaptive octree tree for our subdivision, and then we do some local denoising, then fit a local surface to this data. And we have to measure our error in some metric. So we do a Hausdorff computation, which I'll explain a little later, and then we finally encode the surface. Once we have this encoded surface, we need to reconstruct it or draw it. So we need to create a chi of omega. So this is basically our surface. We approximate chi with wavelets to sort of get a smoother feel to it, and then we display it. I'll show some numerical results and, of course, end with some concluding remarks. All right, so here's our situation. A military aircraft or satellite, and they're really big in unmanned aircraft, so we'll say an unmanned military aircraft will fly over some terrain and collect data. And what it's doing is just a LiDAR scan. So this is just a scanner that hits a surface and basically returns the XYZ coordinate of that surface. All right, so you can have thousands or probably millions of data points, right? Because it's just doing the scanning and it keeps hitting. And you just get a ton of information returned to you. And these data sets need to be processed so that we can then take all this point cloud information of the surface that was just scanned and send it to the ground troops. So then they, on their handheld devices, can look and be like, okay, here's what is up ahead. Here's how we can approach. So they need to know, can we, if there's a bridge in the terrain, can we get a tank under that bridge? Or information like that. But of course, they have limited computational power, and the bandwidth of the information we send is also limited. So we need this encoded really efficiently, so it can get to them in a timely manner, and then once they get it, they can actually view something. All right, so efficient encoding, a suitable metric. So they need to know, okay, what I'm looking at is accurate to within whatever tolerance, but then what metric is that measured in, and then we need fast surface reconstruction or visualization. So the suitable metric is the Hausdorff metric or Hausdorff distance. I'm not sure if you're familiar with this, but basically, so the Hausdorff distance from a set A to B is basically just the distance from A to B, and then we also do the distance from B to A, and the Hausdorff is the maximum of those two distances. So this is it mathematically, a lot easier with a picture, right? There's a picture. You probably can't see that picture, so there's a bigger picture of that same picture. All right, so here you can see that the red curve is a pretty good fit to the data points if you measure the distance from the points to the curve, right? So there's the worst Hausdorff, the Hausdorff distance from the points to the curve is on the left there, the blue line on the left. That is the point that is furthest away from that curve. But the distance from the curve to the points isn't as good. There's a point at the top of that curve there that is pretty far from the data set. So we'd have a large surface to points Hausdorff, but a pretty good points to surface Hausdorff. You're probably thinking, well, surfaces are unbounded, so it's always infinity. But of course, we're restricting our surface to a dyadic cube. Okay? So we want to control both of these. Basically, we call this two-sided Hausdorff, so we want to control each of the one-sided Hausdorff distances. All right, so here are some of our data sets. If you look, you guys can see pretty well, I think. So this is Maple Mountain that they did a LiDAR scan of, and this is actually a pretty good data set. This is pretty easy. Looks pretty dense. You look at it and you can see, oh, this is mountain. You can sort of see the curvature and stuff like that. And also a key aspect is it looks pretty functional, right? It looks like Z could be a function of X and Y globally there. Right? Another data set, this is what I've spent most of my time on, is a building. Again, not too bad. You can make it out, the human eye can make out that yes, that is a building. A couple problems is notice the scan lines. You can see the scan lines, so it's not uniformly dense in any direction. The LiDAR scan creates a scan line. I probably have a pointer here. There you can sort of see like each individual line. So if you sort of over-resolve, you start picking up these individual scan lines, which you definitely do not want to do. Also, there's data up here. I think that is actually part of the building. It's not noise. There's an air conditioner unit here. And really problematic is there is a window here, which creates a hole in our surface. Not only that, but it's not functional because we have the walls are just vertical. So Z is not a function of X and Y. Maybe if we did a rotation, we could get a functional surface and work with that. But we don't bother with that rotation here. All right. This is not turning out well. I should have maybe used more colorful points, but you can see it on that. Which you guys can't really see that, so it doesn't matter. But this is a light pole. Right here, I'll do a little. You can sort of see it. Right here is a light pole. All right, so the fact you can't see the light pole sort of shows you how difficult this light pole is to fit, right? There's very few points here. The points are a little bit noisy. So we don't do a really good job at fitting this light pole yet, but I think the data set is too, like, we're good, but we can't do magic here, right? We need some data to actually fit it. So, but this light pole gives us some problems, but I wanted to mention it mainly because, one, it's clearly not a closed surface. That light pole is like a linear structure, right? There's no inside and outside. Z is not a function of X and Y. It's not functional. And also, the light pole is a linear structure. So how do we handle the linear structures in our data set? All right, so here is our surface encoding algorithm. I'll present the algorithm here, and then we'll go through the details of each little step in the sections or in the slides to come. So the input is basically just the Hausdorff tolerance. So you tell me, okay, I want you to accurately approximate this surface, and I want it accurate to within this specified tolerance. So here's how we do it. We adaptively refine an octree until each leaf node has less than R1 data points in it. I'll explain R1 here in a second. For each leaf node with more than R2 data points, what do? We denoise the data, then we fit a surface to this denoised data, and then we compute the Hausdorff distance. Okay? And we basically repeat 2 until we're done. So while our measured Hausdorff distance is greater than some percentage of our input Hausdorff distance, we refine the nodes where the Hausdorff distance is too large, and, like I said, repeat step 2. Denoise, fit a surface, compute the Hausdorff. And you keep doing that until you're within your tolerance. You're guaranteed to get within your tolerance, right? Because eventually, if you wanted to, you could just refine so much until each cube is so small that the edge length of the cube is smaller than your Hausdorff tolerance, and there's a point in the cube. There, you're done. Right? This is obviously we don't want to do that. It's not going to save us any bits or anything, but it is possible. So the algorithm is guaranteed determining. All right. I put these parameters in here, R1, R2, just as I did to sort of give you an idea that with a program like this, you're going to have a lot of different parameters that you're going to sort of just have to play with and hopefully get a good feel for. So if you give it to someone else, you can be like, okay, here's what this parameter should be, or given this data set, you can estimate what this parameter should be from this data set. So it's not like we just play with it, oh yeah, this looks good, we have no idea why, we'll go with it. But so it's not that bad, but there are a lot of parameters. So the first one here, just efficiency. If you have 100,000 points in a cube, the chances that your surface that you fit to these 100,000 points is going to be within your Hausdorff tolerance, probably not likely. So why waste your time fitting it? Another thing, it's going to take a lot of time to fit that, right? Fitting a plane to 100,000 points is going to take some time. R2, again, you need enough points to determine a unique surface. We pick R2, say around 10. You can fit a plane with, 3 points you need to uniquely determine a plane. But we pick R2 about 10. And then gamma here is we fit the surface, but then we encode it. So we're going to lose some accuracy in the encoding. Right, so if we fit it to within the Hausdorff tolerance, but then we lose something in the encoding, we're not going to be within the Hausdorff tolerance anymore. So this gamma just says after encoding, we're still within this Hausdorff tolerance. All right. So here's adaptive octree, but not really. We flattened an adaptive octree. We call that a quad tree. So it's easier to visualize in 2D. Okay, and so here's our octree, which you can sort of see. You guys like Will Ferrell comedy? Where he says something funny, and then he keeps going with it, becomes not funny, but then becomes funny again. This is like this slide here. We're just going to keep going. Oh, there. So we didn't go too far. But as you can see, our cubes get very fine here. I think this is 2 to the 5 or 2 to the negative 5 or 2 to the negative 6, the size of each dyadic cube. You can't see the points anymore. They're still there, but you can sort of see the adaptive refinement. In this big cube, there are no data points, so why refine? We're doing everything just local. And we have okay, if this guy has a neighbor at, really fine level, we should then refine this guy. No, we don't worry about that. It's not a hanging nodes business. We don't worry about it at all. Okay. So first, most obvious thing to fit is a plane, right? Well, what plane would you fit? You don't want to do a least squares, because that's like z is a function of x and y and a least squares. We don't have the z as a function of x and y. Locally, we just have x, y, z data points. No reason to think that one's a function of other. So here's a general plane equation. And to fit the plane, it's pretty obvious. So L squared of xi, that's just the distance from the data point xi to the plane, squared. Okay, so you want to minimize the distance from the data point to the plane. This sum here is easily minimized if C0, C1, C2, and C3 are 0. So we can't have that, clearly. So we just put the constraint here that the normal to the plane basically has to equal 1, or the norm of the normal has to equal 1. DC represents the data points in the cube. All right, so if you do Lagrange multipliers, technique of Lagrange multipliers, which is obvious, right? We have a constrained minimization problem. What you get is that it's equivalent to analyzing, I say analyzing, I'll explain that here, this covariance matrix. Right? So basically, to find C0, C1, C2, C3, you find the eigenvalues and eigenvectors of the covariance matrix. The two eigenvectors that correspond to the two largest eigenvalues are basically the vectors that span the plane. So that third vector, which corresponds to the smallest eigenvalue, is normal to the plane. So that will give you C1, C2, and C3, because that's the normal vector. So the third vector corresponding to the smallest eigenvalue gives the normal to the plane. Then we just need to find C0, right? Well, you would expect that the average of the data is a point on the plane. So that's how we find C0. So the average of the data is a point on the plane, and then we can solve for C0. This matrix covariance matrix is very important. We use this in all of our analysis, and it involves, we find this, and we get this matrix, then we compute the eigenvalues and eigenvectors. The eigenvectors will be orthogonal and with unit norm. All right. Planar fits, then where do we go to? Quadratic fits, obviously, right? So here we have a few choices, and we have tried all of these choices. And I'll sort of show you the one we decided to stick with, but we need a little analysis first. So here's our 6-coefficient quadratic. Z is a function of x and y. Our factored quadratic, Z is a different kind of function of x and y. Our 9-coefficient quadratic, which is generalization of our 6 coefficient and factored coefficient. And then the most general, our quadric surface. It's not quite, it is the most general, but this guy contains an x squared, y squared term, and this doesn't, but this is still more general here. Okay, so these are our choices. Why did I decide to start writing tildes on top of my variables? This is a good question. This is because, notice I'm assuming here z is a function of x and y, but locally we don't have that. We just have data points in the cube scattered any which way. So what we do first, like I said, we're always using that covariance matrix. What we do first is we do a principal component analysis, which is just finding eigenvalues, eigenvectors of that covariance matrix. And then we can fit a plane to the data points. And then we rotate by this plane to give us our new coordinate system. So x tilde, y tilde, z tilde are the data points in our new coordinate system, and once this rotation by the PCA plane has been done, we can expect that z is now a function of x and y. So locally on each cube, z is a function of x and y after this rotation. I don't need to do this rotation with the quadric surface here because we don't have z a function of x and y, we just have this general equation. So let's look at this guy first. Oh, no, that's not. Let's look at this guy in a little bit. So, question about the linear structures. So there's the imaginary light pole. What do we do with linear structures? Well, we can do cylindrical fits. Okay, so we fit a thin cylinder to the light pole in an ideal world, but it doesn't work very often, but it still theoretically should, and it may someday work. So you fit a cylinder to that light pole, and you have your linear structure taken care of. Otherwise, you'd have to really refine and hope that that light pole is contained in a nice set of cubes going up, and then fit planes to each of these cubes. But since the dyadic cube is so small, the plane actually looks like, if you piece them together, looks like a linear structure. But we don't want to have to go that far down in our tree, right? We'd rather fit up at a much coarser level. So let's look at our plane fitting results. Pretty good, right? So we have, this is taken from the building. Here are data points in yellow. They happen to be near the top of this one cube, and we fit a plane to it, and this is the planar fit that we get. Right? The plane is close to the data points, and the data points are close to the plane. But what about this case here? This plane was also fit using the principal component analysis, just what I showed. So the data points are very close to the plane, as you'd expect, because that's what it minimizes. But the plane out here is very far from our data set. So we'd have a large surface to points Hausdorff error. Right? Our surface way out here, any point, like this point way out here, is really far away from this data point down here. So we haven't minimized our two-sided Hausdorff. We've just minimized the one-sided Hausdorff. And we expect this to happen, right? Because our minimization problem that we set up is only minimizing our points to surface Hausdorff distance. This situation here is not that uncommon. Look at the building, for example. So you have the roof of the building, a nice plane. So you'd figure, oh, I'll fit one plane to that. But what are the chances that that roof fits in one or two dyadic cubes perfectly? Not likely, right? So you're going to get part of that roof in some large dyadic cube, and suppose this is that part of that roof, just part of it is in the cube. So we have this cube mostly empty, data points only here. We fit the plane, and all of a sudden we have a plane going way off the edge of our surface. So if you're sort of thinking, I don't know, in terms of aircraft going in in a city, we fit this surface. We're like, oh, we've got good one-sided Hausdorff, but not two-sided. What this would say is, okay, the aircraft can't go this close to the building because it would hit it. But in reality, it really could get that close to the building because that plane overshoots the building. There's our application. How do we fix this is the question. So how do we take into account the two-sided Hausdorff distance? So what we've given so far has been pretty standard. So this, I think, is sort of a new idea. I haven't seen it before. So what we do is we minimize this first piece. This is the points to plane piece here. And then we minimize this component here. Well, what is this? ds is the surface area in the dyadic cube that is outside of a bounding box that bounds our data. Okay, so if we look back at our picture, we basically put a bounding box here. Right? There's our bounding box, just surrounds the data. And then this surface area outside of the bounding box, but still inside the cube, would be penalized. It's saying we don't want that surface area to exist, so we want this to be small. So if we do this minimization problem, we can fix it. We can move the plane. Actually moves like that. I didn't just draw this, right? This actually did happen with the algorithm. It took a while, but the algorithm didn't take that long to run. It took me a while to figure out how to get it to work, but it did actually work. And the plane moves there. So as you can see, the surface area now outside of the axis-aligned bounding box is nearly 0. So it found the minimization nicely. And here are the Hausdorff distance computations. The data points to surface, that's D to S, for the regular PCA is obviously better because it did the best it could for the regular PCA. But the surface to data points is really bad. With the weighted PCA, it sort of did a nice balance between the two. It did data points to surface and surface to data points, same Hausdorff distance, which is what we want. So it minimized the maximum of the two, which is the two-sided Hausdorff distance, which is the metric we're using. And here I took alpha to be 1, if you're wondering there. I had that parameter alpha there. Okay. So quadratic fits. Here's the most general quadratic fit, and it's sort of the analogous to the PCA situation, right? We just set up this minimization problem here, and we can solve for C0 through C9. Pretty easy. I should mention, just go back here for a quick second, the disadvantage of doing this right here is now this problem is nonlinear, right? So it's not an easy solve. So this is more expensive to solve. We need something like Newton method or something like that to solve this. So it becomes nonlinear. You don't get anything for free. All right, but this here, to solve this, a nice linear solve, easy to do. But what is the problem? The problem is that our general surface is too general. There are too many different kinds of surfaces that this equation can create. For example, if we look at this, here's the corner of a building. It's where the building meets the ground. You can see the yellow data points here, and this was the best quadric surface, right? This is clearly not a functional surface. What can we do with this? There's really two sheets. It doesn't give us a lot of information. Ideally, we'd like to connect those, but there's no real way to do that. You can't say, okay, z is a function of x and y. We take this, complete the square, take the square root, and then take the positive or negative. It's not that easy. You still can get different sheets with this. Right, so like I said, we do not use this in our fitting method. It's too hard to control. Although it's really nice because it's very easy to solve and usually gives a very good points to surface distance. But it's not a functional surface, and we also usually get a pretty large surface to points a lot of times. Like down here to the data points is not that good. So then we look at our factored quadratic and a 9-coefficient quadratic, and we eliminate those from our arsenal as well. What are the complications with either of those? Well, first off, here's the factored quadratic. We need to solve this minimization problem, and this factored quadratic here, it turns out to be a nonlinear problem because of the you have C0 times D0, those paired terms there. So this is nonlinear, and it doesn't give much of a benefit over our 6-coefficient quadratic. In general, there's no reason to expect that it would be better than the 6-coefficient quadratic, so why solve a nonlinear problem when we can solve a linear one? What's the problem with the 9 coefficient one? Well, there are 9 coefficients. Remember, we have to encode these surfaces, right? So we need to encode all of that information contained in those 9 coefficients. We've determined that often the 9 coefficient quadratic doesn't give us enough of a better fit to justify sending those extra bits needed to describe it. So we've decided to go with our 6 coefficient quadratic for our quadratic fit. So it's equivalent to this. We want to minimize the sum over all the data points, zi minus our function of xi, y. Oh, that should be, sorry, that's y sub I, not z sub y. That's weird. I don't know how my brain typed that, but it did. So we minimize this. Notice one thing, that this is sort of like a least squares minimization. Right, but we're hoping that after our PCA rotation that it really is like a distance from the points to the quadratic surface. Although it's not really, we just hope it very closely approximates it. Right, so after the appropriate transformation, the surface is functional. This is why it's better than the quadratic surface. The above equation, easier to solve, it's linear, so this is why it beats the factored quadratic. And the resulting fit is nearly as accurate as the 9 coefficient quadratic most of the time. So here we can do some comparison between these fitting methods. So this is just that same corner of the building where you would expect a quadratic function to improve over just a linear function. So here's the PCA plane that goes through it, just right, principal component analysis. I mean, it does exactly what you'd expect it to do. It doesn't pick up that corner. It can't curve. Here's our quadratic fit. We showed that before. Notice the 2 surfaces. Right? And then our 6 coefficient factored and 9 coefficient quadratic fits all look very similar. And they do a pretty good job of picking up this corner here where the building meets the ground. So those images look about the same. Here's our Hausdorff distance computation. PCA, 6 coefficients. So a couple things to notice. First off, since we are just doing the standard minimization, we haven't added a penalty for the surface area, right? We haven't added a penalty for the 2-sided Hausdorff. We don't have much control over this bottom line here. Right? So let's just look at the top one. PCA is what it is. 6 coefficient is good. Factored a little worse. 9 coefficient a little worse than the 6 coefficient, which you wonder how is that possible, right? Because the 9 coefficient is more general than the 6 coefficient, right? What happened there? Well, I believe this to be the reason is we do the minimization like the least squares minimization, right? But this measures the actual distance from the points to the surface. So like I said, we hope that after translation the distance in the z direction is like the distance from the point to the surface, but hoping, right, we're off by 0.005 in that, or 0.0005 in that desire. Okay, so that's why that is possible. Notice the quadratic does give the best distance to surface Hausdorff, but a larger surface points to surface Hausdorff, but a larger surface to points Hausdorff, and it had those 2 sheets. All right, so this is the one that we decided to stick with. All right, so what about cylindrical fits? So in the light pole situation, we have a linear structure, so we need some linear structure to fit it. The question is, when do we have a linear structure? How can you tell that numerically? So again, we do a principal component analysis. So we look at the eigenvalues and eigenvectors of this SPD matrix, and we look at this ratio here. How big is the largest eigenvalue compared to the size of the largest 2 eigenvalues? And what this is telling you is how much information is contained in the vector v1 as compared to the vectors v1, both vectors v1 and v2. And it can be argued that we should fit a cylinder if this ratio here is above 0.8. How do you argue this? Basically, you can construct a data set that fits inside of a dyadic cube nicely, such that it's right in between being linear and planar. That is, the cylinder that fits the data is as good as the plane that fits the data in the Hausdorff metric. Okay? And we take that as and then we take that example data set, do this PCA analysis on that example data set where they result in the same thing, and then be like, okay, so that's in that case we got a value of 0.08 here. So if it's more linear than that case, we fit a cylinder. If it's less, then a plane is probably a better fit. Of course, you can move the data around in the cube that makes this, not work in general, but that's just the nature of the stuff we work with. Nothing really ever works in general, so we have a hybrid algorithm that sort of looks at both cases, but we'll get into that in a minute. In a second, I meant. So here's our hybrid algorithm. So we have all these fitting options. We have planar fits, cylindrical fits, different quadratic surfaces to fit. We eliminated 3 of the quadratic surfaces, so now we're left with planar fits, cylindrical fits, and the 6 coefficient quadratic fits. So how do we pick which one? So here's our algorithm. Perform the principal component analysis, PCA analysis, so we have our eigenvalues and eigenvectors. If the eigenvalues indicate that we should fit a cylinder by the analysis just sort of argued on the previous slide, we fit a cylinder to the data, and then we compute the Hausdorff distance to that cylinder. Right? So if we didn't fit a cylinder, it's not a linear structure, or if the cylindrical fit did not satisfy the Hausdorff distance, we fit a plane to the data. Fitting a plane, very simple, very fast, so there's no problem, especially after we've done the principal component analysis. We already know what the normal vector of the plane is. So since we have all this information, why not just fit the plane, and we compute the new Hausdorff distance. Right? So here, now we have 2 situations. If both one-sided Hausdorff distances are greater than our tolerance, then we can try to fit a 6 coefficient quadratic to the data. Maybe like it was the situation where we had, just that I showed there, the corner of the building there, where really a higher order fit is what we need. We don't have to refine. So we try that, and we recompute the Hausdorff distance to this new surface. The other situation is where our data points to surface Hausdorff is within tolerance, but our surface to data points Hausdorff is not. So this is where we've minimized the one-sided nice, but we really need to take into account the two-sided. So in this case, if this happens, then we fit a weighted PCA plane, which is that different minimization problem I showed you, where you penalize the surface area outside of the bounding box, or you can do the same, fit a weighted 6 coefficient quadratic, and of course recompute Hausdorff. The weighted 6 coefficient quadratic is the same thing. You just have that ds. Unfortunately, the surface area of the quadratic is a little more complicated to compute, but the idea is the same, right? If after trying all this, you're still not within your Hausdorff tolerance, your only choice is to refine. Okay? One else that we may be missing is, what if our surface to data points is small, but data points to surface is large? Well, then you can just do a quadratic fit, because like I said, our first initial fitting techniques don't take into account the surface to data points distance, right? So if that's small, that just sort of happened by chance. So we don't really analyze that any further. So then we refine and repeat this procedure until we're within our tolerance. So what is our denoising algorithm? Denoising, I sort of, when we started talking about this, I'm like, isn't there some denoising that, like, this is a very old problem. How do you denoise data? There's got to be something out there that is the best or works the best. But it turns out that denoising, it seems, you guys can correct me if I'm wrong, but it seems to be a little bit more of an art rather than a science. I mean, there's no way to really say, oh, this is definitely noise, this definitely isn't noise. So for that reason, this is still a work in progress. Right now, our general idea, fit whatever to the surface, say a plane, and then take the data points that are far away from that plane and draw a ball around them, just like we did here. If that ball contains other data points then we're like, okay, this point out here isn't noise. There's a group of points by it, so we need to do a better fit to it. It's not that this is just noise. On the other hand, if that data point far away from the plane, a ball around it, is empty, then we're still like, okay, that's probably noise. That's just an isolated point. We'll remove that and recompute our fit. And when we remove it, we completely remove it from our data set. But we're still, the question is, really the biggest question is, it doesn't matter, because you can always sort your data points from worst distance to smallest and then look in that order, so that's no big deal. It's how big do we make this circle here, right? So it has to take into account the Hausdorff distance, maybe the size of our dyadic cube in a way. Also, you know, if you can imagine, if this data point was over here and there's a structure here that we fit nice, but we aren't doing any neighboring cube information, so maybe we have to take that into account. So there's still a lot of things to work out with this denoising algorithm. How about our Hausdorff distance computation? This is the most time-consuming portion of our code. Granted, when we get into the nonlinear minimization, sometimes that can take some time too, but in general, but we don't do that often, right? We only do that when we're data points to surface is small, but surface to data points is large. So we avoid that. The Hausdorff distance computation is what's time-consuming. So points to surface, computing distance from points to a plane, that's easy. Points to a cylinder, also easy. But our points to a quadratic surface, we need to do a little work here. So I'll show our idea on the next slide. Surface to points. So now we want, you know, if we have a plane, how do we compute the distance from, you know, all points on the plane within the cube to our set of data points? That's hard. Computing it from cylinder to data points, that's also hard. And from quadratic surface to data points, that's still hard. All right, so we need some way to handle this. And this is the most time-consuming part of our code, so we really want to speed this up. All right, so points to quadratic surface. So here's the idea. I was going to draw a picture, but it would just take way too much of my time, so I'm going to explain it, and hopefully you guys can draw the picture in your mind. So we approximate our quadratic function here with some number of planes, right? So maybe within the dyadic cube, we have z as a function of x and y, so then we have these, say, 4 planes, so then you split the base of the cube into 4, and you have these 4 planes, or you could do 16 or 32 planes, so you approximate that. Then we can use Taylor's theorem to get the largest possible error on each of these planes. So you compute the distance from a data point to the plane, and what is the true distance from the data point to the quadratic? Well, you can get a bound on that just using Taylor's theorem. So once we have these n planes, we compute the distance from the points, data points to these planes, and we keep track of the largest. Right? And like I said, points to planes, that's easy. We can very quickly compute that, and the fact we have to do it 16 times, that doesn't matter too much. You know, it's still 16 times a fast thing is still pretty fast. Okay? Right, and then for any data point that is potentially the furthest from the surface, so you're going to get a bunch of these data points to planes computations, and then you're going from part 2 here, you're going to know exactly what range of true distance this data point could be from the surface. So you take these largest ones with largest possible true distance and sort of their smallest true distance. Any data point that has an approximate, you know, is the range of its true distance is smaller than these furthest ones, we don't have to compute. We just, you know, ignore those. So say 5 or 10% still have a potential of being far, you know, their true distance is the furthest from the surface. Well, so then we just have to take those 5 or 10% and compute an exact distance. So we can do that using Newton's method because we already have a very good initial guess. Right? So that's the general idea. Is take our quadratic, approximate with planes, compute the distance to these planes, keeping track of what point on the plane was closest. Then for the points that are potentially furthest, we then do the exact by doing the Newton's method with already a very good initial guess. So that's our points to quadratic surface algorithm. How about our plane to points Hausdorff distance. I'm only going to analyze the plane to points. I'm not going to do the quadratic surface to points or cylinder to points. So first thing we do, put all these points into a KD tree. If you don't know what a KD tree is, it's sort of like an oct tree, but oct tree, everything's dyadic cubes. KG tree, they can be different size rectangles. This we use other software to do. We didn't have to write this, so whatever it does, it does. ANN, approximate nearest neighbor library, we're about to implement that. It can do this KD tree stuff. And what that allows us to do, it allows us to take a point on our surface and compute the distance from that point to our set of data points, which are now in this KD tree, basically as quickly as you could hope. Right? So then the naive level, which is the naive approach, which is still what our code is doing, because what I'm about to show you is not that easy to code, so I just haven't gotten around to doing it. You then just discretize your plane to some level and compute the points to points distance, and that'll give you basically your surface to points by discretizing your surface. Cheating a little bit, but it gets the job done. All right, so here's our better algorithm. You put an artificial grid on the plane. Right, so you basically are discretizing the plane with some grid. Randomly select a few of those grid cells and compute the distance from the center of each cell to the data points. Right, so now you have this a grid cell which is on the plane, and then you take the center of that cell, distance to the data points. You keep track of these largest distances, right, Dmax. So we selected, say, a random 10, and then we have one largest and 9 other that are smaller. So we keep this largest distance, called Dmax, and we mark the other tested grid cells. And here's the key to the speed up of this algorithm, what I've highlighted in blue here. You can use the triangle inequality to mark the neighboring grid cells that will have a distance smaller than Dmax. So basically you have some grid cell whose center point is farthest from the set of data points. Right? Then you have other grid cells that have distance to that set of data points that is smaller. Right? It's probably the case that if you're right here on the plane and your distance to the data points is small, then your surrounding grid cells also have a distance to the data point is small, and you can naively approximate this by the triangle inequality. So you have this one largest distance, you have this small distance, so create basically a circle around this point, and saying that, okay, any grid cell within that circle is definitely smaller than this distance, so we don't have to worry about computing their point to plane or point to data points distance. Right? So this will hopefully dramatically improve our speed up a lot of the time. And then you repeat this. Pick another random set, and then you keep going until you fit all of your grid cells that you sort of artificially placed on this plane. And one of the favorite things everyone likes to do in my group of working, you come up with an idea and they're like, but what about this? And there's a counterexample. Of course, the worst case scenario, this is not going to help you at all. There's always a worst case scenario. We assume nothing on our data. If you don't assume anything on our data, you can draw points in such a way that will screw up any algorithm. Right? But then you don't get anywhere because you don't do anything. Because you're like, oh, well, that won't work because of this situation. So you got to do something, so you just sort of just do it. All right, so this is our idea for that. All right, what else did I want to mention? I forget. All right. So we finally get to our encoding. This is the main purpose, right? The troops on the ground need this information. We've just fit the surface to the point cloud. Now, how do we encode this surface? So I'll talk about how we encode the planes, because this is very popular. So here's our plane equation. I switched it up a bit just to keep you guys focused. You encode the normal to the plane, A, B, C, and then you encode the D, right? And there are many, like I said, possibly sophisticated ways of doing this. Now, Dan Freeman is a postdoc at Texas A&M, also working on this project, and he was charged with doing the encoding part of this project. So this is what he did at first. But the problem is Dr. DeVore, well, two problems. One is what I'm going to show you, and also Dr. DeVore wants progressive encoding. What's progressive encoding? So here's the idea. We have just fit planes, right? At all levels of our tree, we fit planes. So suppose at some parent cube, we fit a plane. But it wasn't within the Hausdorff tolerance. So we had to subdivide. So now we have 8 children, and we fit planes on some subset of those 8 children, and then we're good, right? Okay, so and then we were in the Hausdorff tolerance, so we send that information. But we actually send that parent's plane information also. We don't just send the information in the leaf nodes. Why? The reason is, and the Army sort of wanted this aspect in our algorithm, is because if the data transmission gets cut off, you want the troop to still have something, right? So if we were just sending the leaf nodes and then it got cut off, they wouldn't have anything, right? They don't have any reconstructed surface. But if you sort of send at each level, you send information, and like, okay, here we have a very coarse surface. Oh, then we get more information, we have a better surface, right? So we're sending all this information, and Dr. DeVore wants to use progressive. That is, if you have a parent plane, you should be able to use that plane's information to help encode the children of the plane. That's the idea. But Dan, he did not do this at first. He just encoded these planes, these normals, and the plane without doing the progressive. But then he realized this problem with encoding the normals. The green is the true plane. The blue is our encoded plane. Pretty good fit, right? But then you put this thing into a dyadic cube. What just happened? Suppose all the data was on that green plane. So the green is the true plane. It fits well, right? And then this blue is close to the green, but it remains in the cube a lot longer. So its plane to points Hausdorff distance just blew up, right? Because we didn't cut it off at all. So now we need some other approach, because a tiny change in the normal can keep our encoded plane in the dyadic cube when really the real plane cut off that dyadic cube very quickly, which is why the Hausdorff, the two-sided Hausdorff, was minimized. So instead of encoding the normals, we instead encode where the plane intersects the edges of the cube. Now the plane intersects at least 3 edges. We don't consider cases where the plane completely engulfs in a face of the cube or an edge of the cube, because we can just shift that and not worry about it. At least 3 edges, right? So we can pick those 3 in whatever method we want. So this is Dan's new sort of encoding algorithm, and he also made it progressive. Right? We can use the information of where the parent plane intersected the edge to sort of judge where the child's plane will intersect that edge. But unfortunately for Dan, Dr. DeVore is now in Paris, and Dr. Gregorn is sort of the head professor on this project, and he showed her this encoding, and she said, oh, I really don't think we should do progressive encoding. And so he was like, what? You know, I was just told, I came up with this non-progressive, now I do progressive, and now I'm not supposed to do progressive. So I'm sitting back sort of just, you know, chuckling a little to myself at this, because it's still not my problem. But then it became my problem. Gregorn then said, why don't we fit a family of planes, so if we nudge the normal, it'll still be okay. And my job is the local surface fitting. So once it was my problem, you know, I had to do something. I did not want to do this extra information. So here's my little contribution. I'll do that in blue here in a second. But first, let's go through how many bits it takes to encode these planes if you're doing the intersection of the edges. The problem is you need to identify what edges that plane intersects. So you label the edges 1 through 12. Does the plane intersect edge 1? 1 bit to tell you yes or no. Does the plane intersect edge 2? Another bit, etc. But the nice thing is, so the worst case scenario is 11 bits, right? Because you can stop after you get to 3. So as soon as you get to 3, okay, yes, it hit 1, it didn't hit 2, it hit 4, and it hit 5. Didn't hit 2, didn't hit 3, hit 4, and hit 5. Right, so then we can stop. Oh, we know the 3 edges. We don't have to send, oh, didn't hit 6, didn't hit 7, didn't hit 8, right? We know that already. Why 11 and not 12, right? Because if you're at 11 and you found all 3 bits, you're done. If you found 2 bits, then you know that it must hit the 12. Okay, so 11 bits, but on average less than 11, right? And here was my a little contribution is there a way to label the edges so that the edges that intersect the plane are most often first in the labeled list, right? Well, I think there is. So here's an example. So here we've labeled the edges 1, 2, 3, and 4. Here's our parent, here's our plane on the parent cube that fits that data there. And when we go to the children, we can relabel the edges because we know exactly how this parent plane goes, so we know where this intersects our children. So we relabel based on that intersection. So we could relabel this 1, this 2, and then when we send this information, we would be like, oh, 1, 2, we're done. Like now we're in 2D, so we only need 2 edges. And we relabeled this one 1, 2, and we're done. We relabeled this one, doesn't matter, because the plane didn't go through there. And then we relabeled this one 1, 2, and 3. Since it's so close, whether it goes through this side or this side, we aren't exactly sure, but it doesn't matter. 2, 3, so it's either we get it after 1 or 2, or we get it after 3. So that's sort of the progressive encoding. We reorder the edges based on the parent's information. Okay. All right, so now we've encoded and we've sent it. How do we reconstruct it? So here's our reconstruction algorithm. So we have an encoded surface. The first thing you have to do is you have to create a characteristic function that approximates this surface. Then do a wavelet approximation to this characteristic function, smooth our wavelet approximation, and use a marching cube algorithm to draw this wavelet approximation. So the question is, we have a characteristic function of omega. What the heck is omega? So omega is anything we choose. It's some three-dimensional object such that the boundary of omega is the surface we want. So here are our two choices. We can globally determine an inside and an outside of the surface, then take omega to be the inside. Right? So think of the building. Everything in the building is inside. Everything outside the building is outside. We have 1 and 0, and then when we change from 1 to 0, that is our surface of the building. Right? Or we can compute a distance field, just a Euclidean distance, on some uniform grid of points, and take all points within epsilon of omega, take omega to be all the points within epsilon of the surface. Okay. The disadvantage was the first method. I don't like the first method because it's given me many headaches trying to compute, is we don't have closed surfaces, right? There's a window in the building. The light pole, there's definitely no closed surface. So what do we do when we don't have closed surfaces? I don't know. They come up with a bunch of stuff, but none of it works in general. On the other hand, the disadvantage of the second method is you created an epsilon wrap. So really your surface is now epsilon away from your true surface. So you introduce this little bit of air. Right? But it's a little more robust. So we do the uniform grid to create this discrete chi of omega. And so here's our first determining inside and outside. How do we do that if we determine that we do have a closed surface? Compute a distance field on a uniform grid. And then you initially assign, basically this is the ground, right? Z is 0, so this is the ground. The ground we consider inside, and a point at the surface, or at the very top of our cube, everything's in the unit cube, right? We assign that a value, this is value 1, that a value 0, and then we propagate these two values in the order of largest to smallest distance values. This is important. The propagation in this order is important, because otherwise you get your 1, you get your inside to the surface, right? And then for whatever reason there's a little hole in your reconstruction. What could happen is then it gets through that hole and then propagates and ruins everything, right? Now all your zeros become 1s and everything's ruined. But if you propagate in order of the distance, basically you move a little bit up and you move a little bit down, move a little bit up, move a little bit down, what will happen is they should meet the surface at nearly the same time. So even if you get a little bleed through the surface, the fact that the other hit that at around the same time will stop it. Right? So this is very, very important. In our numerical results, often we get this bleed through. So we need this sort of to stop it. Epsilon wrap is simple. Just compute a distance field. Anything within your epsilon is a 1, everything away is a 0. Okay. Wavelet approximation, like I said, we're just sort of studying on this. We have a function called chi of omega, and we just do a wavelet approximation of that, which Why we do that is it creates some smoothing. We can choose a smooth wavelet and also quantize, and there may be some PDE we can run that smooths it further, but we haven't gotten to that step yet. And then our surface rendering, we just do a marching cubes algorithm, which you may not be familiar with. You can Google it and it'll tell you a bunch of how a marching cube worked. Basically, you have to give it an ISO level, right? Well, our ISO level of 0.5 makes sense, right? Because we have a 1 and then it goes down to 0, but the wavelet is continuous, so it'll go continuously from 1 to 0. So an ISO level of 0.5 will give a pretty nice surface. All right, so here, let's do a couple of movies. Everyone likes movies. So that's sort of our algorithm in work there. So that's the initial plane, and we adaptively do the octree, and then we fit the planes at each step. All right, next movie. This is the same thing without the grid on there, but also it shows you us computing the inside and outside. So here, that's sort of the initial light green, blue points are inside, and we propagate it and notice that it stops at the surface. Sometimes that's more luck than anything else. Here's our wavelet isosurface reconstruction. It's not that pretty, but that's partially our visualization technique. We can improve upon this. This is in MATLAB, but we have some better OpenGL stuff. All right. Notice here we cheated, right? I'm not going to show you, but we cheated. We took out the window of the building because the window made it a not closed surface. So we just we filled in the window. Right. So now let's look when we do have the window. Here's some. Here I'm just showing you plane approximations. I have others, but this was the easiest to show right now. So see the data points in here are plane approximations. Notice we get some irregularities. I mean, it's very tricky because the data points don't fit into the dyadic cube the way you want them to. You know, some are, sometimes the nice data is right on the boundary of two cubes, so then you get these two planes, and it's very tricky for that reason. But you can still see that you can get the surface, even though you have these planes sort of sticking up with the sparse data and stuff like that, you can still at least get a general feel for what the surface is, and we've dramatically saved on the number of bits here. And this is the epsilon wrap of the surface. Right, so we just need to work on smoothing that a little more, but you can see how we've wrapped the surface that we created. And here's results from Maple Mountain. Here are the planes. Why I'm showing this is because you can sort of see now how the quadratics will dramatically help, because you have the nice, sort of hills, or basically would be a good quadratic function. So there's a planar fit. Continue thing. I don't know why it stopped responding. Did my movie screw it up? All right, let me try to exit this here. I don't know. I don't know why it's stuck. My computer seems a little frozen. If it starts working, it starts working. But I can explain a little bit. So next couple images are this, but zoomed in a little bit. You see the planes, how there's, in the data points, there's a rough fit. But then you get to quadratics, and you can sort of see how it's a much better fit, because it smooths things out. You guys would just have to visualize that and just test your visualization techniques. And then I had a conclusion slide, which basically said we developed a surface reconstruction algorithm where we took into account the two-sided Hausdorff distance. We also took into account various fitting schemes where we did cylindrical fits, quadratic fits, and planar fits. We were able to encode the surface efficiently. And then we also were able to reconstruct the surface using sort of a wavelet approximation. Future work, where do we want to go with this? Well, we have to implement some things yet. That Hausdorff distance computation, that fast one that I showed, haven't implemented that yet. We definitely have to implement that. That's the first thing. We're would also be nice if we could take into account some neighboring information. Right? So we have a cube and it has some data points in it, but maybe these data points are really part of a structure that's mainly in a cube right beside it. You know, how do we take that into account? This is hard to do though, because remember, it costs computation time every time you have to look things up, especially in an oct tree that's, you know, refined so that you can have a bunch of small cubes next to a large cube. We can have more complicated structures, but then how do you encode these more complicated structures? And then also in future work, we'd like to look at how can we smooth our wavelet approximation a little better. And that is all I have. Yes, yes. This is a very good question, and currently we don't really have a way of gluing them together very well. Hopefully the data is nice enough that our local fits will, because the data is good, we get a good glued together thing, but this is not guaranteed, of course. Some of that is just, we can't help it because the data is ugly, but the only real method we have is just that wavelet approximation. Once we get that wavelet approximation, if we can then smooth some things a little bit, because if you have that wavelet approximation and you have those, it's not glued together nicely, you're going to see some, you know, derivatives are going to be ugly there. So there is some PD smoothing stuff that we can run. I don't know with wavelets. I haven't ran that with wavelets, but you basically have like a level set function and run this stuff which smooths your surface. The problem is that's pretty expensive. At least my implementation of it was expensive. But those are our ideas so far. It's basically post-processing that we try and glue things together to give a more appealing visualization. But yeah, we're still working on that. That is definitely very tricky. It's the price you pay, right? If you want to look just locally, have everything local solves, then all of a sudden, you know, then it doesn't match together as nicely.
Another question is, like you mentioned, taking the neighboring information into account. Actually, that's also like, yeah, for the fitting criteria, we're using just the hostile and some other surface reconstruction, because sometimes, for example, we also, when we scan data, we also have the normal information on that point. So you could probably have more than just the position, but also the normal points.
Yeah, see, unfortunately, we don't have normals. We've requested that the scanning equipment that they're developing has this normal information in it, but right now it doesn't. And then we have some algorithms that then estimate the normals, but these don't work. They aren't real robust. They haven't been written by us. Not that I'm saying we would write a robust one that works. I'm not saying that at all. I'm just saying they haven't worked for. We haven't worked on it, but we've gotten some pretty good stuff like Seagal and some other group, Hong Kai's group out at UCLA has given us this, and still the normals will flip often just because the data is so sparse that they turn, like when you go from the edge of the building to the roof, it'll then flip in. So we don't have any ways of getting reliable normals as of yet. But
so if you have normal, you can have the data somewhat like less dense.
yes, absolutely.
So the question was that if suppose you have those normals,
Mm-hmm.
the way that you fit it into this
Yes, and the way I think we would do that is we wouldn't do a PCA plane then. Right now we're just taking data and we just do a PCA plane, and then that gives us normals. But if we actually had normal information on the plane, we could do some hybrid between PCA, but also take into account that the average normals of all these points in this direction. So our plane that best fits them should also point in that direction. So that's how we'd probably implement that. Is our planar fit would take into account what the normal of the plane should be.
How long does it actually take? How many points do you take?
Yeah, so the data set I'm working on is like 100,000 points. 60,000 or something like that. But they can get a lot bigger. And it actually doesn't take too long, except for the Hausdorff computation. But when we speed that up, I expect it to be quite a bit faster. But like on my laptop, it'll run it, and it'll fit nicely within 5 minutes down to the finest level on that building data set. But then we have Maple Mountains a little bigger, and it takes a little longer. But not like days or anything like that. And it's not what?
Not interactive.
The goal is that it eventually maybe could be. And I think right now on these data sets on a bigger computer with a little cleanup, it could be. Yes, the local fitting could be, because you have these leaf nodes, and then you just do a local fit on these leaf nodes that you're not taking in any account any other information other than those data points in the local leaf nodes. So that's definitely parallelizable, and we've thought about doing that, but not quite at that stage yet. But the Army would eventually like to do that, and they'd also like to get into a point where they zoom in, like, so they're like, oh, we want to know more detail in this area. So you zoom in, sort of like Google Maps does, and show the fit there. But then you globally go out and look at, so you sort of refine and coarsen all sort of interactively at the same time. And then you definitely need some parallel computing to do that.
Did you think about fitting beyond just one leaf, for instance, using splines for the entire surface? We've definitely thought of the spline thing, and we haven't gotten there quite yet. Just like a lot of it's this neighboring information we don't have very nicely, for one, and then it seems like every time we go to a step where add more complication, something more complicated, then all of a sudden we present more problems than we fix a lot of times. But we have discussed that.
I'll stop the discussion, but can continue because there's still refreshments in the back.
Thank you.